Okay, today we are going to skip out of the tutorial for a moment. We're going to look at something known as momentum and angular momentum. So it's actually something that's much more profound and important than most people understand, because the idea of linear momentum and angular momentum is actually quite vague, to be honest, even for linear momentum. So today, instead of doing the tutorials, let's take a deep dive into what is the actual principle and physical meaning, theoretical meaning of linear momentum and angular momentum. So let's talk about linear momentum. So linear momentum is denoted by the quantity L, right? Where L is equals to mass of the particle times V. V as in the velocity of the particle. So today, just to be clear, we are still doing kinetics of particle. So we are only concerned about the momentum of a particle, not about. Now, when we talk about linear momentum is equal to m times velocity of particle, this is how you describe the linear momentum. So what is actually the physical meaning of momentum? Now, a lot of people have this misconception. They think that momentum is actually the description of the tendency of an object to retain its state of motion. The answer is no. Momentum is not a measure of the tendency of the object to stay in a state of motion. That is basically inertia. That's mass. Mass is basically the tendency of the object to stay in motion. Momentum, on the other hand, is just a quantity. It's just a quantity of an object moving in linear fashion. It's just a motion quantity that we are both interested in. And we can define this by saying that when an object has a linear momentum, it has a certain motion in the linear direction. That's what we can know when something has a non-zero linear momentum. And according to Newton's second law, we know that force is equal to mass times acceleration, right? And there's actually another form for this thing. Force is also equals to the rate of change of linear momentum. This is the definition of force. Force is equals to ma, force is equals to rate of change of linear momentum. And if you were to do a bit of manipulation to this quantity here, to show the dt up, put an f here, and it's equals to integrate dr. So if I were to integrate this from T1 to T2, and at T1 I have a momentum of L1, at T2 I have a momentum of L2, this thing will become L2 minus L1. And this term here is something that we denote as impulse. Right, impulse. So from this derivation, what we can see is that impulse is equals to the change in momentum. So basically, the definition of impulse is just integration of force with respect to time. That is what impulse is. And please take note, first of all, this force here might not be constant with time, so please do not try to replace this with just F times t. This force here might be a function of, let's say, a linear function, or it might be even a quadratic or a polynomial function with respect to time. So it's actually incorrect to state that F is equals to F times dt integrate is equals to Ft. Okay? This term is only equals to F times t if F is constant with time. Now, so what's the main purpose of me going through this? First of all, you should understand, momentum or linear momentum is a quantity obtained or is available in a moving object in a linear motion. So if you want to have a very quick change in momentum in a very small period of time, you need a very large force. Hence, force is defined as rate of change of momentum. So it also means that what is basically the property of an object which is moving in a linear motion. So that's what the definition of linear momentum is. So this is quite straightforward. Most people understand what's going on here. So I'm just going to put all this term on one side. So as for linear momentum, we have momentum term, linear momentum is equals to mass times velocity of a particle. And then we have the term where force is equals to rate of change of linear momentum. And from here we can derive the idea where impulse, or integrate F times dt from a certain time from T1 to T2 is equals to the change in momentum across this time frame. That is what we know. Now, that is linear momentum. How about angular momentum? Now, this is where people get funny. So, what is actually the definition of angular momentum? So, without knowing any prior knowledge, the angular momentum of a point or a particle was defined by this equation, where angular momentum h is equals to mass of the particle times r cross product with v. Alright, pause. What does this actually even mean? So, let's look at the comparison. If linear momentum describes the property of an object in a linear motion, angular momentum describes the property of an object in an angular motion. In other words, what we are concerned here is the property of an object going in circle, but that doesn't make sense because, first of all, we are talking about angular momentum, and it seems that not all motion on Earth goes in a circular motion. So the first question might arise then, is it possible for a linear motion object to have an angular momentum? In other words, is it possible for a particle that's moving in straight line to actually have an angular motion? Think about it. Well, the answer is yes. So why is it so? Now, before we answer all those questions, let's first do the robotic way and just try to understand how to calculate linear momentum. First of all, to calculate linear momentum, if I give you this object, I give you this particle here, and this particle is going in this motion, for example, and I ask you to calculate what is the angular momentum of this particle, the answer is you can't actually find the answer to that. Because to answer something known as angular momentum, to find something known as angular momentum, you need to have a point of rotation. Okay? In other words, linear momentum depends on where your point of rotation is, or your defined point of reference. That's what it's trying to say. So, for example, if I have an object here, I have an object denoted by this black color, what is it called, point here, this object here, and let's say this object A. Object A is going in a velocity in this direction here, v. Now, if I ask you what is the angular momentum of this object, the answer is that you can't find it. It's impossible because I do not give you a point of rotation. As I said, angular momentum describes the property of an object, of the rotation property of an object. And if you want to define something known as rotation property, you need to have a point of rotation, right? Because all rotation motion must always have a center point of rotation. So in this case, if I ask the question, what's the angular momentum of point A? You can't answer. Now, if I ask you the question, what is the angular momentum of point A about this point O here? Then you can find the answer. Because this point O is so-called your point of rotation. So how do you link the idea of rotation with linear momentum? We will deal with that later. But if today I pose you the question, how to find the angular momentum of A with respect to O in terms of the rotation point of O? Now the answer is actually very simple. What I can do is just first of all, I'll apply this equation. M is the mass of the object MA. R, which first, and V is basically the velocity of the what is it called, the object at the very moment. R is actually the distance or the displacement of the particle with respect to the point of rotation. So in other words, this vector here is R. And to be more exact, it's actually RAO. Okay? In other words, angular momentum, so what we have learned so far, angular momentum describes the angular rotation properties of an object. And since we are trying to describe the rotation property of a particle, you must have a point of rotation. And that particular point of rotation can be any point. It actually describes the rotation property of an object about any point. So in this case, if you want to find the rotation angular momentum about O, we are trying to find the rotation property of point A about the center O. And the formula says is equal to M times RAO cross product with V, where RAO is the displacement of the particle with respect to the rotation center, and V is the velocity of the particle itself. Now, to calculate this thing, it's tough, because it's cross product. We don't want to use cross product, so I always have a shortcut. So how do you use a shortcut for this cross product? So please be careful. There's actually two methods to do it. I always recommend you to use either of this method instead of using the cross product method. The first method to do it is basically X. So the first method to simplify this equation is to firstly extend the velocity vector. So we have the velocity vector here, right? First of all, I extend it first. Extend it both ways. I extend it. The second step was to find the shortest distance, not displacement, shortest distance of this extended velocity to the rotation center. So in this case, the shortest distance will definitely be defined by this green color line here, right? Because it's 90 degrees. I'll repeat, first of all, you extend the velocity. Secondly, you draw a perpendicular line, or the shortest distance line, from this extended velocity to the rotation center. And you basically calculate what is this length. And we denote this length here as RAO prime. And please take note, I say length, so it's a scalar quantity. And this equation can be can be simplified now into mass times R prime AO scalar times the absolute value of the velocity. In other words, you have the velocity, right? You find the absolute value. Means if it's negative, you put it positive. The absolute value of the velocity. And then at the end here, in terms of the angle, is always either plus minus k, where k is a unit vector in the z direction. So where is it plus, where is it minus? Now it is positive if, now this is big, okay, it is positive if this motion, this object, have a tendency to rotate in a counterclockwise about the origin here. So look at this, it's very interesting, okay? Point A is moving in this direction. So it means that it is moving in this direction, and think about this very carefully. If suddenly a string appears between point A and point O, what will be the subsequent motion of the particle? It will actually rotate, right? So this is basically what it means by the tendency of the object to rotate about O. So in this case, when the velocity is pointing in this direction, the tendency of the object to rotating about O is actually a counterclockwise direction. So in this case, it should be a positive k. If today the velocity is pointing in this direction, there's a tendency for you to rotate about this center O in a clockwise direction, and hence it's a negative k. Okay? Let me repeat. So how do you calculate the shortcut measure, the shortcut method for what is it called angular method? First of all, you denote, you extend the velocity, and you find this shorter distance between the velocity and the center line. And you want that as R prime AO. And multiply R prime AO and mass of the particle, and also the absolute velocity, in other words, the speed of the particle. Multiply them together, and then denote the direction by observing the velocity at the center point. Now the velocity is going here, so if there is actually a string that suddenly appears between A and O, A will rotate this direction. So we know that A has a tendency to rotate in this direction, so it's counterclockwise, so it's positive k. If today, point A, the velocity of A is pointing in this direction. If today velocity of A is pointing in this direction, and if suddenly a string appears between A and O, we know that it will still remain a horizontal motion until the string becomes taut, and it will still rotate in this direction. So it has a tendency to rotate in the clockwise direction. Then you put a negative k. If today, our point of reference O, our rotation or motion O, is actually somewhere on top here, if assuming that our O is actually somewhere on top here, then it means that this velocity in this direction will have a tendency to move in this direction, right? So it means that it's actually a clockwise motion. So if today our O is in this position, this k will be a negative k. So that's a shortcut to actually look at this equation here. But of course, you can always use the cross product method and see if it's y is equal to 6. Now the other method to do, there's another method to solve this cross product method. The other method was actually, instead of what is it called, shifting the displacement, this displacement is actually equal to RAO. What I can do is that, first of all, I can resolve this velocity component. I can resolve this velocity component to two directions. One direction, which is perpendicular to the displacement, which is known as I'll just put R1, okay, V1. And the other direction is basically in, let's say, this direction. And the original velocity is actually equal to V. So in other words, the second method to solve this equation is basically just resolving the velocity to two directions. One is perpendicular to the displacement of the point from this center rotation. The other one is basically perpendicular to it, so it's parallel to what is it called, parallel to the displacement. Now, once we have these two terms, I could immediately denote this term as, I think I'll use the previous option, m times the absolute value of RAO, in other words, the magnitude of RAO, just make it positive, even it's negative, it'll be positive, and the absolute value of V1. So you resolve this V into two directions, and one perpendicular to it, you take the absolute value, multiply by the absolute value of this thing, in other words, the length, okay? And then, in terms of the direction, it is plus or minus k, use the same understanding. If this thing is going here, you have a tendency to rotate in this direction, about this O here, so it's a counterclockwise, so put a positive k. So in this case, it's a positive k. If this thing is moving the other direction, it has a tendency to rotate in a clockwise direction, so it's negative k. If O is on top and V is in this direction, this object will have, this particle will have a tendency to rotate in this direction, so it's a clockwise direction, so it's negative k. So it's a very visualized thing. So look, we have used this method to determine the plus or minus k. But in this case, because my O is here, my V is here, so you have a tendency to rotate like this. So it's positive k. Now, if you don't recall, look at what I just said. Angular momentum basically describes the tendency of an object to describe the property of an object, the rotational property of an object. Now, to answer our previous question, can a linear motion establish a rotational property? The answer is yes. Look at this question. Particle A is having a linear motion, right? Linear motion to the left. However, it has an angular momentum about O. Why? Because it has a rotational tendency. How do you prove this rotational tendency? By imagining if suddenly there's a string that appears between A and O. What will be the subsequent motion of A? The subsequent motion of A will be a circular motion about O. So in other words, this motion itself consists of a portion of a rotational motion about O. How do I prove that this understanding is correct? I can use another extreme. The other extreme basically was assuming that today, point A was moving in a velocity in this direction. Okay? And I want to find the angular momentum of this point with respect to another point O, but this O is actually parallel to the velocity. Now see what happens. If I were to use this method to what is it called, solving, right? Let's try to use one of this method to solve it. So I use the first method here. So I know that this distance is my RAO. Right? Makes sense, right? So if I use this green color method to solve this equation, my answer will be equals to m times my RAO. How do I find the R prime AO? First of all, by extending my by extending my velocity. So if I extend my velocity, I realize that I actually cut my rotation point. And the shortest distance between this extended velocity line and the center of rotation will be 0 because it cuts it, so the shorter distance is 0. So in other words, this is 0. And in other words, the angular momentum of this particle about the point O here is 0. Now, does it make sense? Think about it. If today a string suddenly appears between A and O, what will be the motion of A subsequently? 0. Because the string will immediately cancel out all the vertical horizontal motion, and there is no vertical motion left to continue to rotate about O. So in other words, there is no rotational property, and hence it will actually have a 0 angular momentum. So that's what my angular momentum. Angular momentum basically describes the rotational property of an object about a center. How do you visualize this rotational property? By imagining that suddenly a string appears between the center of rotation we define and the object itself. If after the string suddenly appears, the object stops and did not rotate, it means that it has definitely an angular momentum of 0. If after you establish a string, the object is rotating counterclockwise about the defined center, it means that you will be positive k in terms of the angular momentum. If it's clockwise, it's negative k. That's how you take a look at it. So that's how we prove that there is actually angular property, angular rotational property in every single motion that's possible, even for linear motion. So that's the first thing I want to point out. So now, since this is angular momentum, and you know physics is amazing, so angular momentum is basically like a brother of linear momentum. So anything we have here, we can also describe in an angular form. So this is basically what we know as angular momentum. So as you know, linear momentum is L equals to mv. Angular momentum is equal to m times r displacement cross product with v velocity. Now, how about F? So for linear momentum, we got force acting on the particle is equals to rate of change of what is called linear momentum. So in angular momentum, we have the torque that's acting on the particle is equals to the rate of change of angular momentum. So, and again the question asks a bit, what is actually, how do you calculate torque? Now first of all, it's impossible to calculate torque without a reference point, right? It's impossible to calculate torque without a point of rotation. So, here's how it goes. Imagine this. I have a point A, point A. And let's say I have a center O. Okay? Now, apparently, if today I have a force acting in any direction, force acting here. This is basically the summation of forces now. So, how do I find the torque about this center O here? As I said, to find the torque, you need a center. So, the formula is actually equals to, if F is equal to MA, if this is equal to MA, then the formula for torque is actually equals to F, is it equals to, my bad, you cannot do this singularity. So, torque can also be expressed in terms of force, and it can be expressed as R, AO, cross product with the force that's acting on particle A. So in this case, RAO is basically the distance, the displacement here from O. RAO, this. So how do you calculate this? So same thing again. How do I calculate RAO times force? You can actually use this understanding, right? First of all, what can I do? I will extend my force vector by extending, and then find the shortest distance. Define this shortest distance as RAO prime. And then this thing can be calculated as RAO prime times the magnitude of force. Don't care whether it's positive, negative, it's positive. And the K can be plus, minus, or plus or minus, depending on whether the force is going in the, is acting in the what is called counterclockwise or clockwise motion about the defined center. In this case, the force is acting like this. So it's sort of like encouraging the object to go in a clockwise direction. So it's supposed to be a negative torque. The truth is that you should use a right-hand grid rule, but then I just want to prevent from using the right-hand grid rule. So if you want to use a right-hand grid rule, right, you actually use something like this. So this is the direction of the force. It turns like this about the center here, so then it's inside, so it's negative K. But to prevent confusion, let's just use the visualization method. If the force is pushing this direction, it's sort of like encouraging this block to rotate clockwise about O. So in this case, you put a negative for the top term. If the force is pointing in this direction, it is encouraging the object to rotate in this direction about the counterclockwise direction about O, so you can put a positive here. So it depends. Now, let me repeat what I'm trying to do here. First